Okay, so we started discussing this PN junction part 2 already. We talked about what happens when you apply an external bias and how to change the depletion weight in the N region, P region, and total depletion weight. We just basically have to add the reverse bias with the built-in potential, or for forward bias, you have to subtract it. We then moved on to basically we discussed this already, what happens to the band diagram when you have forward bias. We also discussed this very quickly. I just wanted to quickly do a recap in case you had any confusion. This is basically the distribution of minority carrier concentration throughout the PN junction region. All right. So let's see. This is the metallurgical junction, which is x equals 0. This is the edge of the PN junction in the edge of the space charge region in the N region, edge of the space charge region in the P region. All right. Let me just zoom in a little bit. Okay, so these 2 points are important. These 2 points represent, by the way, before I talk about these 2 points, this is N type. So electrons are majority here, right? And due to diffusion, electrons are injected across the space charge region to the P region and vice versa. From P region, holes are injected to the N region. Now, the moment these electrons get to the P region from the N region, they start as minority carriers in the P region. They were majority in the other side, but here they're minority. So gradually, their concentration will reduce as you go deeper into the P region. Here is why. Because the P region is full of holes, and the electrons can easily recombine with holes as you go deeper into the material. Closer to the boundary, they have just arrived from the other side, so the concentration will be much higher. But as you go deeper into the material, they will gradually diminish. The same argument could apply to the holes that are coming from the P region to the N region. So they will be maximum at the edge, and then they will gradually go down as you go deeper into the material, right? Any problems so far? And I told you that this might sound disjoint and without any subsequent discussions on it, but these diagrams will be instrumental and actually crucial to understand bipolar junction transistors. So there we'll add one more thing to it, because bipolar junction transistor will have NPN and PNP, one more layer. And the interaction between this, diminishing concentration of minority carrier will be a key aspect of the device principle. Okay, so just making you aware of this concept. Now, we are ready to move to the next slide and talk about the next concept, which is small signal model for diode. I think you have already worked with diodes for your other code. There were some issues. I spoke with the TN. I received some feedback from the students as well. Thank you for that. Hopefully, you are having some good experience working with diodes. All right. So you already know how the IV looks like. There is a turn-on point, there is a breakdown voltage and whatnot. We are just gonna cover this from the theoretical side very quickly because there is a actual practical aspect associated with it as well. So in electronics, we often try to make a conceptual model for any device that we encounter. It could be MOSFET, BJT, diode, or something more complicated. We try to represent the features of those devices using simple circuit components. And theoretically, you should be able to represent any electronic property with resistors, capacitors, inductors, because they are the fundamental components. That's the concept. At least that's the hope. You may not be able to figure out how exactly. So we often use some tricks and some approximations to do so. But theoretically, everything has inductance, capacitance, and resistance. And merging these three in a more complicated way, you could represent any complex phenomena. So this is one example. And obviously, as you can imagine, the easiest possible example of an equivalent circuit, because this is the easiest possible device, right? We try to replicate different phenomena within the device structure with either a capacitor or a resistor. So imagine, here is a principle. If there is some sort of hindrance for electrons to flow or holes to flow, we represent that with some sort of resistance. Isn't that logical? If there is some sort of lag or a delay between something getting charged up and charged down, we represent that with capacitance, as you can imagine, right? So similarly, you don't see a lot of inductors here because these devices typically don't have much inductance to deal with. But whenever you have devices that have magnetic properties, you bring in inductance to represent those electromagnetic interactions. Okay, especially in some RF devices, you'll see those kind of scenarios. Are you guys with me? Okay, now let's see. So in a diode, this space charge region, as I told you, it governs a lot of the working principle of the diode. There are two capacitance levels associated with it. Number one, so when you have separation between positive and negative charges, this is more like a parallel plate capacitance. So, and that occurs at the junction of the p and n type material. It's called junction capacitance. I mean, easiest possible way to name something. All right. One more thing, when you apply a bias, like a positive bias or negative bias, basically this space charge region either increases or decreases in size, right? So something happens. So it changes. You either have uncover more charge or less charge. So basically, these charges will respond to the applied voltage. So that's what a capacitor does. The capacitor generates or puts in more charge or less charge, depending on what happens to the voltage across it. Is the voltage is gradually increasing or decreasing? So whenever there is a dynamic change in the voltage, the capacitor can respond. But if the voltage is DC, no change, the capacitor will not respond, by the way, right? So this could be represented with another capacitance. So junction capacitance is one. The other one is diffusion capacitance. Basically, we name it diffusion because the additional layers appear because of additional diffusion. So more charges diffuse away when you apply negative or say reverse bias. So that's why we say it's a diffusion capacitance. So diffusion capacitance represents the extra charges that appear when you apply extra bias. Junction capacitance represents what you already have just because of having a junction. There you go. You have these two components already covered. Oh, by the way, I forgot to say, these 2 points are the end points of the diode. So I'm trying to convert this structure into resistors, capacitors, and possibly other things. Okay. So we have already discussed the reason for adding 2 capacitors. What is this resistance? And I'll talk about this right now. There is a reason why we're calling it a small signal model. So typically, we can bias the diode at a given point. Imagine with a DC voltage. Imagine you apply a DC voltage across the diode, and this is the DC voltage. Are you guys still with me? So we treat the DC and AC signals a little bit different way, because when you apply DC voltage, the capacitors will not really respond. So you'll probably miss out on the properties of capacitors, but they will show up whenever there is any dynamic change. So when we deal with electronic devices, we have to care about both static and dynamic mode. So whenever things are changing, whenever things are stable, we have to treat both. So to be able to capture all the aspects of a device's property, all the capacitors, all the resistors that we should consider, we should definitely consider the DC as well as some AC. All right. So again, so when we apply a DC voltage like this at the IV property of diode, you get a certain current out of that diode, right? Have you seen this IV property before in the last lecture? Give me 1 second. Let me go back here and draw it for you one more time. So current versus voltage property, forward biased situation, there is a diode drop or turn on voltage beyond which the diode starts providing you current in an exponential way. And in the reverse bias sense, there is almost no current, almost negligible, until a certain point when there is a breakdown, and then you have a really, really abrupt switching current. Okay. Very simplistic overview of a diode IV property. Oh, I meant to go here. Okay, this is, as I told you, probably it's exaggerated just to show you that there is something. It's not completely zero. Okay, so we are dealing with the forward bias situation here. So you apply a forward bias voltage, DC voltage, and for that there is a corresponding DC current. Okay, and then if you superpose an AC signal on top of it, right? So imagine you have a DC voltage. some DC voltage, VDC. And on top of it, you have an AC signal. So that AC signal will take it a little bit up and a little bit down. So increase the voltage a little bit, decrease the voltage a little bit, okay? So that means from this point onwards, you'll move to the right and move to the left. Move to the right and left, slightly. Does that make sense? Why are we mentioning small signal here? Because if the amplitude of this is too much, right, there is a possibility that you basically will go out of the on state to the off state, even reverse bias. That will be extremely difficult to make any sense of. So we want to make one stable DC point and stay within the same mode. If it is forward bias, let's stay within the forward bias and see the property around it. Okay. There is another reason to make small signal, by the way. So when you have current versus voltage somewhere, say something like that. I'm just randomly drawing something here. If you take di over dv, you guys know v equals I. I'm just showing a very simple relation here. So resistance equals v over I, or conductance, whatever. Resistance equals v over I. So practically, we could say it's dv over di, right? Are you guys with me? So if you take di over dv and the inverse of it, that gives you the resistance, by the way, right? So similarly, here, to figure out the inherent resistance, so there is a resistive nature in the diode. Anything has a resistance except for superconductors, okay? Anything. So it could be ferroelectrics, it could be metal, it could be insulator, it could be semiconductor. It has a resistance. So we're trying to figure out this value. I mean, you see in most equivalent circuits, they will always start with a resistance. It has to be resistive, and then some capacitors. Go ahead. Oh, no question. Yeah, so there will be a resistance and then some capacitors. So how do we figure out how much resistance to add? If I add too much, it will defeat the purpose. If I add too less, it will be underwhelming. So we have to kind of estimate how much resistance will this diode provide, okay? So for that, notice, if it were a straight line like this, doesn't matter where you take the slope, it's always going to be the same. It's a constant slope. If you have a curve, which is something like that, you can still approximate a slope and more or less be okay with it. But if you have an exponential curve, you see the point? An exponential curve will have high resistance here, extremely low resistance here, and so on. So there will be huge change depending on where you're looking. Does that make any sense to you guys? So here, it's almost no resistance. Here, there is very high resistance. So this is not doing a justice, but I think, let me try to show you somehow. Here, it's very steep. Here, not so much. So the resistance levels will be different if you measure in different situations. So we have to make sure we choose a DC bias. And for that DC bias, we stay within a very small region. That's why small signal. If you go to a very large region, it will basically be meaningless because it will show you very high and very low resistance and give you an average. You don't get the actual point, okay? So you have to choose where are we going to operate the diode in. We're going to operate it at 1 volt. Sure. Let me figure out in the vicinity of 1 volt, how is the resistance? Are you guys all with me so far? So remember, it is being designed for a DC operating point, say 1 volt. We choose that DC operating point because in different operating point, the resistance will be like extremely different from each other. So I choose one DC operating point, and then I impose a superimpose a small signal AC voltage, which takes me around the level and helps me get the slope around it and estimate the resistance. That resistance could be RD. Are you guys still with me so far? Okay, so if you change your DC level, that will also change because there is an exponential dependence here. So devices that show this type of dramatic changes in IV property, they have to be treated in a small signal fashion more often. Okay, so we know how RD is calculated, how CD is done, how CJ is done. We can now calculate one more resistance, which is basically a non-ideality. So imagine when you talk about this RD, which is the diffusion resistance, which is within this section, we are assuming that this extra N and P regions are kind of ideal. They are like not adding any resistance, but that's not true. Basically, there will be some, no matter how small, some resistance in the neutral N and P region as well. So we sum them up into one series resistance. Sorry, not this one. This one, series resistance, RS. Okay. So there are 4 components in the diode model: RS, RD, CJ, CD. And this is a small signal model that we use. Now, with all those discussions, I see that you are a little bit bored. One of the reasons why you don't need to worry about it that much in modern times is because we have much better, much more accurate and highly detailed model now in our modern age. You don't necessarily need to go for an equivalent circuit model anymore. There was a time, imagine you were trying to solve a complex circuit where there will be diodes, resistors, capacitors, and other things. And you're using KCL, KVL by hand, like piece of paper. And you're solving equations, right? How can you solve the diode equations with the others? Super complicated. In that case, just represent the diode with a circuit, and then you do circuit solving. Haven't you done so in electronics 1 and other things where you learned KCL, KVL? But now we have simulators that are so powerful that could even deal with superconductors, for example, like super complex devices and circuits, right? Because all those hard equations, they could be internal to the black boxes. So you drag and drop diode, MOSFET, BJT, you connect them with whatever you want, resistors, capacitors. It will solve it for you and give you the results. So nowadays, you need less and less exposure to this type of small signal model. Does that make sense? I'm not asking you not to pay attention. I'm giving you some hope that if you find it, okay, man, come on. This is kind of lame. But don't worry, people have done the hard work for us so that we don't have to. Right? Are you guys all with me so far? So in every lecture that I take, after this BJT and then MOSFET, I'll show you the equation, the circuit, the small signal equivalent circuit, but you don't necessarily need to basically deal with it in your life, in your career. You have models, better models available. All right, with that, I'm going to move on to the next topic, which is the tunnel diode. Very interesting kind of diode. And this is basically the last topic of diode related to our diode lecture. Okay. How many of you remember N plus semiconductor and P plus semiconductor? What is the difference between N and N plus? Silicon. Heavily doped. Thank you. When you dope a silicon, say, imagine this is conduction band, valence band. An N-type silicon will be something like this, where the Fermi level is closer to the conduction band. But this is N-type. But N plus would be so heavily doped that the Fermi level has gone above the conduction band or at the conduction band. Okay. So a tunnel diode, remember I had a lecture on tunneling and I told you how crazy it is. You throw a particle at a barrier, it passes through the barrier as if there is no barrier, right? Those crazy effects are used in modern life. And I told you about tunnel microscopy. Did I talk about electron tunneling microscopy? Probably. That are used, and we use them to see really tiny devices at nanoscale. This is another example and real application. Tunnel diode, a diode that uses tunneling as a mechanism to operate. And let me show you how that works. Okay. Please pay attention, and hopefully this will be quick that way. So let's work together on this. Let's pay attention. This is an N plus semiconductor. How do you know that? Fermi level is above the conduction band. This is a P plus silicon. How do you know that? Fermi level is below the valence band. Okay. And this is a PN junction. How do you know that? We have connected them, and basically there is a gradual connection, space charge region. So super simple PN junction, similar to what we did before. Okay. And if you want to learn to draw this from scratch, sure, let me draw it from scratch very quickly. So we always start with a flat Fermi level. Now you need a where P, okay, N was here. So N and P. So for N region, I'm going to first draw conduction band. Typically, we usually draw the conduction band above the Fermi level, but here we'll draw it below the Fermi level. So this is N plus. And then for P plus, we'll draw the valence band above the Fermi level and then the conduction band. And then we'll add them really nice with nice and smooth curves to represent the gradual potential change. All right, so that's what you had here. Any problem so far? Okay, and just to, I mean, this is a side note. This is taken from the textbook, so I had to keep it there. But just to explain that, remember in my lecture, I showed you this type of a diagram where a particle was thrown at a barrier. And I told you that there is a finite probability that it will transmit through the barrier. So there was a transmission or tunneling probability. Anybody remembers that? And the barrier was what kind? Rectangular barrier. Why? It's easy to deal with in math. Rectangular barriers are easier to deal with because you have 0 here, 0 there, and a constant here. Okay. But if you had a barrier like this, man, it's super complicated to deal with. In math, in hand calculation, by the way. In simulators, you use supercomputers, fine, no worries. Just go ahead and do it. Okay. All right. There is another kind of barrier. So practically, this is more like a barrier. Let me show you here. Imagine you are an electron sitting here. Better color, red. You are an electron sitting here, and you're looking at the other side. You're trying to get to the other side. But there is a barrier. This is an energy barrier, right? So practically, a better approximation of this barrier will be to use a triangular barrier rather than like a rectangular barrier. That's what the textbook wanted to tell you. Okay, so the space charge region here is more like a triangular barrier. Okay, anyways, so setting that aside, it has no other implication, by the way. Let's move to the next slide and show you how this device uses tunneling to achieve something unusual. Okay, you might be wondering, why would we have diodes? Why would we go for tunnel diodes? Because that gives you something that nothing else can give you. Okay, so there you go, enough motivation. So at zero bias, let's zoom into this one. What we have just worked on together is at zero bias. How do you know? This could be a question for midterm. How do you know this is zero bias? Fermi levels are aligned, right? Remember I told you that as long as you have a flat aligned Fermi level, that represents no voltage. If you apply positive voltage or negative voltage, they will move in one direction or the other. Remember? And we had several slides and discussions about it. One thing that I just realized that I told you about, but then I didn't finish. Remember I told you that we don't draw the Fermi level within the space charge region? Remember I told you that? Have you seen other band diagrams as well, where we don't draw the Fermi level within the space charge region typically? You see that here as well, here. So we don't draw anything here inside. Any reason why? Can anybody tell me the reason? Anyone? Why don't we draw the Fermi level within the space charge region? So the name should, what is the other name of space charge region? Depletion region. Thank you. Yes. Why do we call it depletion region? Because it is depleted of carriers. Fermi level represents, how far the electrons will populate an energy level. If there is no electrons to populate anything, what is the point of showing a Fermi level? Does that make sense? So within space charge region, there is no free carriers available. So we don't really draw any Fermi level within the space charge region. Does that make sense to you guys? No. Okay, in case you had question. If you don't have that question, that's okay. All right. So we start from, let's try to make the IV. At zero voltage, you have zero current. Simple. Let's apply, notice, slight forward bias, a little bit of a forward bias. Okay. So what is forward bias? This is N, this is P. When you apply positive to P and negative to N, that's forward bias, right? So if I apply a negative bias to this, using our simple analogy that we talked about in one of the previous classes, right? It's as if you have added a balloon to the Fermi level, helium balloon. Negative bias is like adding a helium balloon, and positive voltage is like adding some weights. Didn't I talk about it? Okay, so what happens to the Fermi level to the left? Folks, it should go up. Please respond. If you respond, it will be quick, and hopefully you'll never have to think about it again. And if not, then I'm sure you're going to run into confusion. See, these are taken from several pages of textbooks. So this slide is worth at least 2 pages of textbook. It could be more. Like they will talk about blah, 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 and you'll be lost while you're reading it. What? Come on. And there is no animation, right, in textbooks, so it's very difficult to follow. I wish at some point there will be like just videos text instead of textbooks, and that will explain everything, show you the 3D animations and everything. So learning will be much easier. But until that happens, we have to live with what we have, okay? So please pay attention. This was our Fermi level here. As we apply a negative bias, this Fermi level should go up with respect to the other Fermi level. Now, as the Fermi level goes up, notice, why have I made it gray? Because I want to indicate that there is a lot of electrons available. So this is your conduction band, by the way. This is Fermi level. Electrons should be available up to the Fermi level and above the conduction band. So these electrons are ready to conduct because they are already above the conduction band. Am I making sense? So they're already above the conduction band. So, well, as this Fermi level goes up, the overall energy of these electrons will go up a little bit, right? The Fermi level is going up. So all these electrons will become more energetic. So they will hate it. Nobody wants more energy, right? So electrons say, hey, my energy is increasing. I'm unhappy. How can I reduce my energy? So suddenly, these electrons will see the other side. Folks, take it. I mean, I have to go back and forth. So you have to continuously look at it. Notice, previously, it was perfectly aligned. This is an idealistic scenario, but it was perfectly aligned. So even if these electrons felt like we have more energy, they couldn't go to the other side at least, because the other side was also filled with electrons. Does that make sense? This gray, why is it filled with electron? Because this is Fermi level. Any energy level up to Fermi level would be full of electrons, right? So this is already filled. So these electrons, even though they liked, maybe they wanted to go to the other side, there was no room for them. Perfectly blocked. Now, when this thing goes up like this, all of a sudden there is an offset. You see this region? There is an offset. The electrons notice that, hey, my energy has increased. My energy has increased, but there is empty room over there, and I could possibly reduce my energy by going to the other side. But they cannot go to the other side. Why? Because there is a barrier. This is an energy barrier. You see that? There is an energy barrier. If they have to go to the other side, to the other material, they have to go above the energy barrier and go to the other material. Are you guys still with me so far? This is unique, by the way. You haven't asked me the question, but it's really strange that I'm talking about it that way. Let's get back to conventional p-n junction. When it talked about electrons going from one side to the other, notice electrons could go from here to the other side because this was positive or forward bias. So the electrons could go from one side to the other side. But notice they were going from conduction band to conduction band. Isn't that right? Do you remember that? Can you relate it? But here, I'm talking about a situation where electrons, I mean, instead of going from here to the other side, which is a really, really high gap to cover, they're just considering, should I, instead of going all the way up, is there any way I could just tunnel through this? Am I making sense? Right? So it's just considering, but the cost doesn't, it's prohibitive because there is too much energy to tunnel through it. Cannot do it. And I told you that the tunneling probability, that's why I had that equation in one of the previous lectures. Tunneling probability is exponentially dependent on what? The barrier width. You have probably don't remember, do you? So this is the barrier width, say T. The lower the barrier is, the more probable it will be to have tunneling, right? And exponentially more probable, not just a little bit more probable. So if you could reduce the barrier slightly, there will be a huge change in the probability of having tunneling eventually, okay? So these electrons will consider tunneling And some of them will, because tunneling probability is never zero. Some of them will. So they will tunnel to the other side instead of going all the way up and to the material, because there is less motivation there. I mean, I'm already having more energy. If I have to go to the other material, I will need even more energy. I'll be even more what is the point, right? Rather than doing so, the electrons will try to stay in the same energy level and get to the other side. Okay, so some tunneling will occur. Are you guys all with me so far? Why do we talk about tunneling here and not in the other material? Because of the n plus p plus argument, there is a possibility to have the conduction band of one material interact with the valence band electrons in the other material. Remember, let me go here again. Conduction band, valence band. What's there under the valence band? Can anybody tell me? What is there under the valence band? Electrons, protons, what? Electrons. Electrons. Basically, there is electrons. What's there above the conduction band? There could be electrons as well. I told you holes don't exist, right? Whenever there is some missing electrons, we call them holes. But it's essentially all electrons. But for the regular diode, the situation was as such that it was easier for the electrons to deal with other electrons in the same band, conduction band, and holes to deal with the holes in the valence band, by the way, right? But here, because of this n plus p plus situation, we skewed the band diagram so much that these electrons have motivations to interact with the electrons in the valence band instead of the conduction band. That's the unique design here. Are you guys still with me? Okay, so what if I apply even more forward bias? So what happens then? See, it goes up even more. So previously there was some offset. Now there is a lot of empty offset. So all of these electrons are welcome to come to the other side if they can tunnel. Okay, so what happens there? You apply more voltage. The more voltage you apply, the more offset you create, the more electrons tunnel, so the current increases. Do you notice that? The more voltage you apply, more current you get, because more electrons can tunnel through. You open up more and more offset. Are you good so far? Okay. What happens here? Just notice the curve. All of a sudden, it stopped increasing and started reducing. Wow, why is that? Why is the current reducing here? Any idea? Notice, as we keep applying more and more positive voltage, this Fermi level will keep going up. And all of a sudden now, see what happened here? Just notice between this and this section. Did the overlap increase or decrease? Why can't the electrons go from here to here? What's wrong with this zone? Can anybody remember the name of that zone? Forbidden band, remember? Or band gap. So there couldn't be any electrons at all in this region. Between this region, there couldn't be any electrons, right? That's quantum mechanically forbidden. That's why it's called forbidden band. So the electrons can only use this section. So there was a time when you had a limited sections to use. As you keep increasing the voltage, gradually you had more region to use, so the current increased. And then if you keep increasing the voltage even further, you will come at a situation where you'll have even less space to use for the electrons. And if you keep applying more and more voltage, this will keep going up, and at some point the offset will be lost. Does that make sense to you guys or no? Can you visualize this? I wish I had an animation or something like that that shows this is gradually increasing and the offset is gradually decreasing. Are you guys all with me so far? Okay, great. And please think about it at home. And if you run into any confusion, I'll be happy to go over this again. But the point is, look at the IV. Your current is increasing gradually with voltage. and then it is decreasing with voltage, which is surprising. And I'll tell you why that is surprising later on. But let's finish the discussion. Let's see what happens when you keep increasing the voltage even further. Let's do that. Then the Fermi level has gone up so much that now there is no overlap. There is no overlap at all. All on a sudden, these electrons will no longer plan on tunneling to the other side. Okay, they will no longer plan on tunneling, because where can they tunnel to? They cannot tunnel to here. No. So then they will start behaving like regular PN junction. Now this is like regular PN junction. These electrons can get to the other conduction band if you provide them with enough energy. Okay, so now they're going to follow the same IV that the diode follows. Simple. Any problem so far? Don't worry about this yet. Up to this point. So in a tunnel diode, if you look at the IV, initially the current increases with voltage, then it decreases with voltage, then it again increases with voltage. It's a very strange IV, right? Can anybody see what's unusual here? As an engineer, you should start looking at opportunities in something weird. Like there's a lot of opportunities in weird devices. This was the very first observation of a negative differential resistance, negative resistance. Here is how. I just told you, IV. If you take an IV curve here and take di over dv, which is the slope of the curve, and take an inverse of it, what do you get? Resistance, right? So have you ever seen an IV curve? If for some reason, if you see an IV curve like this, that implies it has what? Negative slope. Negative slope means negative resistance. What does negative resistance mean? Wow. Positive resistance means it will hamper the flow of current or something like it will hinder the flow of current. How will negative resistance like come into picture? Remember, we have to say this is negative differential resistance. Okay. So basically this device in this region gives you positive resistance. If you take the derivative, that's why differential resistance. If you take the derivative here, it will give you di over dv negative. So in this region, it gives you NDR. Just if you Google with NDR, you get a lot of hits in Google. Negative differential resistance. Okay, and these devices are used to make oscillators and chaotic circuits and other things, like very useful devices that enable a lot of applications that could otherwise be impossible. Okay, this is not the only device anymore. There are other devices that give you NDR, but these are rare. It's not like, oh, every other device will give you NDR. It's very difficult to make. There was a time when people used to use circuits, specialized circuits, to create an effect similar to NDR, to make oscillators. You go to the lab, you use oscilloscope. I need this sinusoidal wave. Sure, who creates that sinusoidal wave so nicely? There are oscillators inside those devices. Somebody had to think about it, right? Even if we don't, somebody had to think about it. So oscillators are used to generate oscillations, as you can imagine. So these oscillations are created using many a times using NDR devices, negative differential resistance devices, right? Otherwise, just leave with DC current, 1 volt, like toys, right? Just put in some batteries, just work with it. When you start making oscillations, then things become interesting. All right. Anyways, so the last point before I conclude this section is about what happens when you apply reverse bias. That's the only slide about reverse biasing. Super simple. It's even more easier to tunnel in reverse bias condition. So what happens when you reverse bias? This was N, this was P. So if you apply positive to N, negative to P, that will be reverse biasing. Okay. So when you apply positive bias to the N side, I told you that applying positive bias is like adding a weight that will pull down the Fermi level. So the Fermi level here will go down, and Fermi level on the other side will go up. And here, notice these electrons, all of these electrons will just look at the other side and see, oh, hey, we could just tunnel to the other side and be happy. And they will tunnel to the other side quite easily. So, and notice, will there be any situation where there will be something of an overlap and then the overlap will be gone. Or if you keep applying positive voltage over and over again, this will keep just going up, going down, and this one will keep just going up. So it will always be favorable for the electrons to tunnel to the other side. I guess I confused you. My point is, for reverse biasing, you'll always have to apply positive here and negative here, right? If I increase the reverse bias amount, this Fermi level will keep going down, and this Fermi level will keep going up. So that means this electrons will always be more and more motivated to come to the other side. Don't you think that's the case? What is the problem with the other tunneling? Because there was a case with overlap, and then all of a sudden it went inside the forbidden band. So it had to stop. But here you don't traverse through the forbidden band. Basically, you tunnel from valence band to the conduction band. There is no forbidden band to deal with to the other side. So in the reverse bias condition, basically the current will keep increasing exponentially. That's unusual, not like a diode. So it doesn't stop. One of the useful properties of diode is blocking reverse bias. So when you apply opposite bias, it would block. But this diode will not do it. Okay, but it is useful for other things. Obviously, not every device will do the same thing for you. I guess all with me. All right. Okay, so that's tunnel diode, a very interesting concept, an unusual concept that demonstrates that quantum tunneling actually works. Now, I have a question for you. See, there is a hidden questions already, and the less question you ask, the less you learn, and that makes my job easy, by the way, because if you don't ask me, I could just skip and move to the next. Done, syllabus over. But I'm almost tempted because this is important. Why didn't you ask me, can we create a similar effect? Or why can't we create a similar effect with a conventional p-n junction? What is so special about p plus n plus? Why did you start with n plus p plus? How did you know? We covered this concept in one of our lectures and spent some time, but then we moved on. We never realized that this could be so useful. How many of you remember the term one-sided diode? You don't remember? Okay. All right. I hope I have the lectures. Don't worry, it's worth it to take the time to go back and see. It's probably going to be 2 more minutes, but let's see. No, not this one, not so 10. So I meant to go to 10. I want to show you something. Yeah, this slide. See, there was a slide. Title, one-sided diode. And by the way, you have a midterm on Tuesday. Okay, so there you go. You have to practice more, okay? Don't feel like I understand everything. But, okay, let's see. Why do you think, do you guys remember this diagram that I drew? Basically, we started with this diagram. We started the concept with this diagram. N-type and P-type. And then this represents the space charge region. I told you, how can I squeeze it? How can I reduce the size of this side or the other side? And if you forgot, like, listen to my recording. So the point is, you can reduce it by doing what? And I showed you that here. If you take P plus, wherever you take heavily doped semiconductor, the space charge region in that side will be skewed, like tiny, narrow. Am I making sense? On the other side, it will be as usual. So if you have heavily doped semiconductors, the space charge region will be narrow versus wide. Are you guys still with me? Okay. Notice in a conventional p-n junction, this was the space charge region. You have electrons sitting here. Okay. The electrons want to tunnel to the other side for some reason. What's wrong here? You have a barrier that is super thick. You have n region, p region, space charge, huge. It's like, okay, forget about tunneling, man. I don't care, right? It was impossible. Who can make this thin? Who? N plus, P plus. If you take just P plus, this was one example. It made one side super thin. What if I took N plus as well? This would make the other side super thin. So then overall, you have a really thin barrier between P and N type. Does that make sense? Can you relate? There was a reason why we had all on a sudden a lecture on one-sided junction, because this is used, this concept. That's how people think of new ideas. They don't just, oh, today I woke up, I'll think about a tunnel diode. Never gonna happen, okay? So you keep connecting the dots, one idea with the other, and eventually you come up with something useful. Okay, so there you go. That's why we started with N plus P plus, because if there is any way, people thought about, why would we wait to go from this conduction band all the way to the other conduction band? Can we not just tunnel through this? Yeah, what is the problem? The problem is this space charge region is too thick. What makes it thinner? Heavily doped. Let's try. So you do an experiment. You do this IV measurement, you see this strange result. Like, oh, wow, you have negative resistance. Just imagine the headline, by the way, in the scientific community. Scientists discover negative resistance, right? Okay, so in recent time, when I was a PhD student, there was a lot of hype, and there is still a hype about negative capacitance. If you want, you can Google it. Negative capacitance is a more recent concept that was discovered. There's a debate among the scientists about the possibility of getting negative capacitance and whatnot. And the implications are tremendous. If you have negative capacitance, imagine you apply 1 volt, you get 1.5 volt. Like, so you're creating voltage out of nothing. It's almost that crazy. So there is a Nature paper, you can search proof of negative capacitance, and there will be a Nature paper coming in. So Nature is like the top journal in the world, right? Nature Science, the top journals. So if you have this type of a breakthrough, you have a major story. Anyways, let me move forward, and this is the last slide, so I'm taking it slow. Don't worry. I know that we're almost there. We're good with the midterm exam syllabus. So junction breakdown, we have probably already dealt with breakdown, Zener diode and whatnot. Reverse bias is not indefinite. Diodes, regular PN junction diode will block the reverse bias voltage up to a certain point, and then it will break down. It will give you tremendous amount of current. But there are two kinds of breakdown. One is reversible, the other one is not. Reversible meaning you can let it break down, but if you remove the voltage, it will just behave as if nothing happened, right? The breakdown is temporary. But there is another type of diode, another type of breakdown, which is permanent. It's as if like you have destroyed the device. You have just literally broken down the diode, okay? So that's called avalanche breakdown, and the other one is the one that is repeatable is called Zener breakdown, okay? And the physical mechanism behind it is very different, and these descriptions are basically copy-pasted from the textbook. If you read them, you should be fine. You don't need to read the entire passage. But I'm going to explain it. Let's do that. So this is a PN junction diode, as you see. And it's, how do you know it's reverse biased? I mean, do I need to tell you more? This is electron, and there is a huge built-in potential, like built-in potential has been amplified. That means you have added reverse biasing, okay? So you have reverse bias condition. Notice, well, it's possible for you to start creating electron hole pairs inside, say, the valence band. Are you guys still with me? Okay. Electron hole pairs are always randomly created because of thermal process, okay? One electron getting out of one location creates a free electron as well as a hole. So that location that it broke out of is a hole now. And the electron that broke free, for any reason, is a free electron. So you create an electron hole pair somehow in this region. And all of a sudden, that electron will see there is another way to thin down the barrier. If you squeeze it too much, then the distance between them, don't give up. Maybe confusing you. So if you keep applying more and more reverse bias, this space charge region could gradually thin down. This potential could gradually thin down. As you can, I don't know if you can see that. Let me show you. So if you have a slight reverse bias versus a heavy reverse bias, say here. Notice, simply by geometry, just notice that. You squeeze this section, instead of here, you have much less barrier here, don't you think? Squeeze it too much, that it becomes more possible, more probable for the electrons to actually tunnel. So all of a sudden, the electrons will start tunneling. And, well, if you remove that reverse bias, this balance, these bands will realign again, and tunneling will be over. So when the tunneling starts, it suddenly leads to a really high current. But when the tunneling stops, it goes back to normal. Okay. But in the avalanche breakdown section, well, this is the deeper understanding of what actually happens in. But in practice, you can measure the IV and see the breakdown. There will be huge surge in current beyond a certain voltage. And in datasheet, they will talk about how much breakdown voltage it can handle. So in avalanche breakdown, apparently, this is P-type, this is N-type, and there is a space charge region, and we have been dealing with it for a while. This is reverse bias, and let me explain what this thing is. This is the concentration of minority carriers. This is in region. So P is the number of hole in minority. So P is the number of hole in the N region, which means this is a minority carrier. So this is a minority carrier concentration. Okay. So a similar diagram as I showed you in the very first slide of this lecture, remember? But that was opposite because that was forward biased. So for forward biasing, you start here and then you gradually go down. Start here, gradually go down. For reverse biasing, you start here and go down to 0. For reverse biasing, start here, go down to 0. Again, why? Because when you reverse bias, you basically, kick out any carrier from near the surface to the other side. Let me explain that. This is P-type, this is N-type. When you reverse bias, you apply negative bias here and positive bias here. Okay? Does it make sense? So, let me start here again. So this is, say, let's use the same one, P-type and N-type. Okay. So electrons from N-type can come here to the P-type and then gradually diffuse away. But why did the electrons come from N to the P in the first place? Because they were repelled by the forward bias. Say, when you apply negative to the N-type, electrons are repelled and they go to the other side. But when you apply reverse bias, meaning you apply positive here, electrons are never repelled. Basically, they don't want to go to the other side. They're attracted to the opposite direction. Making sense? So basically, that's why these distributions are exactly opposite. That's what you see here. Just wanted to quickly explain this. But my point is, notice that there are some minority carrier here and almost none here. Similarly, some minority carrier here and 0 here inside the space charge region. So there is a difference still. There is still a difference in density. And whenever there is a density difference, there is a chance of diffusion, no matter how small. That's why in the reverse bias situation, you don't get any current at all. But you can still get some because of this difference. There is still some diffusion current, some, very little, okay? But the thing is, the moment one of these carriers diffuse into the space charge region, there is a huge electric field already built in, electric field in the space charge region. That electric field takes over and it accelerates that charge. Hear me out. So you just have to take the first step and get to the electric field. The electric field will automatically accelerate you. The moment you get into the electric field, it's like a vortex. It will accelerate the charge. And then all on a sudden, that carrier can hit some existing atoms. So there are some bonds already in the silicon structure. If you accelerate an electron or a hole, say, it can hit other electrons and kick them out of the bond. And those electrons, like chain reaction for nuclear fission, chain reaction, right? You hit one uranium atom with a neutron and it breaks down, creates other neutrons, and it hits other uranium and it's breaking down, and then it goes out of control and burst. So similarly, one electron, if it is sufficiently energetic, and how does it become energetic? By the heavy electric field. It can hit other electrons, kick them out, and those electrons can kick other electrons out and create a situation where you have an avalanche. You know what avalanche is, right? So basically, you can relate to the name. All on a sudden, it's uncontrollable. It's typically an unwanted situation because you cannot really recover from this because there will be a lot of broken bonds in the silicon structure. Making sense? You might wonder, why isn't it happening in the forward bias situation? Because in forward bias situation, just take a look at the number, the amount in terms of voltage for the reverse bias. It could be really high. Typically, this breakdown occurs at a very high voltage. Okay, we for forward bias we typically don't use that much high voltage, and even if we do, the chances, the space charge region is narrow. It's not really wide. For reverse bias, the space charge region increases, so there is a lot of chance for you to create and generate this chain effect. Okay, for forward bias, space charge region is narrow. You don't have to go up to that level of electric field, so no chances of having this type of a chain reaction. Okay, so that's the underlying mechanism, but you are dealing with them in practice, I hope, in the lab, right? Okay, that concludes the diode lecture. I don't want to, I mean, I have lecture 12 uploaded, but I don't want to start with that today because, again, there will be a huge gap between it. So it doesn't make sense. We can start fresh in the next class when we meet in person together. But before that, good luck with your midterm. And if you have any questions for me or anything that you're needing help with, reach out to me. Okay. All right. I'll be here in case you have questions, by the way. You don't necessarily need to go sooner. Give me 1 second.